Hello my dear students, today I will be discussing about springs. What is springs and what are the different types of springs? Okay, a spring is a device in which the material is arranged in such a way that it can undergo a considerable change without getting permanently distorted. Okay, all of you know, I think, this spring. You can see here, this is the springs. It is nothing but a material. It can undergo a considerable change. When the load is removed, it comes to its original shape without getting permanently distorted. Okay, and it is also used to absorb energy due to resilience, which may be restored when it is required. Okay, mainly these springs are used in railway carriages, motor cars, scooters, motorcycles, and rickshaws, etc. So a spring performs some of the functions like to absorb shock or impact loading as in carriage springs, to store energy as in clock springs, to apply forces to and to control motions as in brakes and clutches, to measure forces as in spring balances, to change the variations characteristic of a member as in flexible mounting of motors. So these are the different applications of springs, and these springs are usually made of either high carbon steel or medium carbon alloy steels, and also phosphorus, bronze, brass, etc. The quality of the spring is judged from the energy it can absorb. For example, in a watch, you can imagine in a watch the spring is wound to absorb strain energy. This energy is released to run the watch when the spring regains its original shape. It is thus obvious that a spring which is capable of absorbing the greatest amount of energy for the given stress is known to be the best one. This is about springs. Okay, then we will see what are the different types of the springs. There are actually very different types of the springs. So the mainly these two are the main two types: helical springs and carriage springs or leaf springs. Again, these helical springs are classified under two categories, that is closely coiled helical springs and open coiled helical springs. Helical springs are nothing but it is a torsion spring and made up of a wire coiled into a helix. You can see here, this is helical spring. Okay, a helical spring is a length of wire or a bar wound into a helix. Okay, so mainly there are different types, mainly two types: closely coiled helical springs and open coiled helical springs. First, let us discuss about closely coiled helical springs. In a closely coiled helical spring, the spring wire is coiled so close that each turn is practically a plane at right angles to the axis of the helix, and the wire is subjected to torsion. Okay, that is in the case of closely coiled helical spring, and here the bending stress is negligible as compared to the torsional stress, because torsional effect is more here compared to bending stress. Okay, again these closely coiled helical springs are means it is subjected to different types of loadings twist. So we will discuss first what is the effect of closely coiled helical spring when it is subjected to axial loading, and then when it is subjected to axial twist. Okay, so first we'll discuss about the closely coiled helical spring subjected to an axial load. Okay, this is the closely coiled helical spring and it is subjected to the load, axial load W. This is the radius R and this is the diameter of the coil, that is D, the spring coil. Okay, now see, let us consider a closely coiled helical spring subjected to an axial load as shown in the figure. Here you can see that is subjected to the load. Okay, let D, small d, is the diameter of the spring wire and r, that is mean radius of the spring coil, and n is number of turns of the coils, and c, modulus of rigidity for the spring material. This is also sometimes represented by g also. Okay, w is axial load on the spring, then tau is maximum shear stress induced in the wire due to twisting, then theta is angle of twist in the spring wire, and delta, that is deflection of the spring as a result of the axial load. So you should know all these terms while solving the problems, and there are different formulas. We'll see that, we'll go through that. You have to remember all those formulas to solve the problems. Okay, now the first case, closely coiled helical spring subjected to an axial load. What happens here? First, because of the load, it causes a twisting moment. How in the bending, there is a bending moment, like that in the springs there is a twisting moment that is given by T is equal to W into R. Okay, same thing like bending force into perpendicular distance, that is equal to bending moment. Like that, here twisting moment is equal to, that is T is equal to W load into R. R is radius here. In the bending stress it was the distance, perpendicular distance. Here it is radius. Okay, so this you should know. Twisting moment is given by the formula T is equal to W into R. Then also you can twisting moment, you can elaborate it how it is, because it is given by the equation pi divided by 16 into tau into d cube. Okay, it is derivation is there, that is not required. I have written directly the formula. This you should know. Okay, so twisting moment is equal to pi divided by 16 into tau. Tau is shear stress into d cube. Okay, diameter. Now T is equal to WR. We know that, but that is load into radius. Okay, substitute here is equal to pi divided by 16 into tau into d cube. So now this you can write in terms of any equation. Like if you know this equation, you can find, if it is asked to find W, you can use this formula. If it is asked to find the radius, you can use this formula. If it is asked to find the shear stress, you can use this formula. So in terms of any one of the value, you can write this equation. So remember this, WR is equal to pi divided by 16 into tau into d cube. Okay, or W is equal to pi divided by 16R into tau into d cube. Or if you can write in terms of tau also, tau is equal to WR into 16 divided by pi into d cube. Any in terms of any this specific load or radius, shear stress, you can write the equation. Okay, next one we will see torsion of the circular shafts. In the yesterday's practical class, I have mentioned what is torsion and what is the torsion equation, right? What is the torsion equation? I have told T divided by J is equal to, I have written yesterday G, you can write G or also or C also, C theta divided by L. Okay, there is one more term is there, is equal to tau divided by R, but we use only these four terms. So T divided by J is equal to C into theta divided by L. So write in terms of theta. What is that? Theta is equal to T into L divided by J into C. We know T. What is T? T is equal to W into R. Substitute that. L is equal to 2 pi Rn, length of the wire, that is 2 pi Rn, is divided by J. J is nothing but polar moment of inertia, that is pi divided by 32 into d raised to 4 into C. So if you simplify this, you get theta is equal to 64 WR square N divided by CD raised to 4. So theta is equal to 64 WR square N divided by C d raised to 4. Okay, this is angle of twist. Theta is angle of twist. So after that, there are some more formulas. Okay, the length of the wire is given by the equation length of one coil into number of the coils. That is the length of the wire. Length of the that is equal to length of one coil is 2 pi r. Number of the coil is into n. So the length of the wire is equal to 2 pi r n. That's why here it is written in this length is equal to 2 pi r n. Okay. Next, we'll see what is the deflection of the spring. So deflection is given by r into theta. Okay, what is r? R, just write like that. Theta is equal to, we know here, 64 w r square n divided by c d raised to 4. Okay, so simplify this, you get into theta, 64 w r square n divided by c d raised to 4 into r. Simplify this, you get 64 w r cube n divided by c d raised to 4. This is the formula for the deflection. Okay, then the strain energy that is stored in the spring, so that is given by the formula U, that is energy is equal to half into W into delta. U is energy, W is load, and delta is deflection. Okay, one more formula is stiffness of the spring, that is given by W divided by delta. Okay, where W is just substitute that, we know delta, right? Delta is equal to 64 w r cube n divided by c d raised to 4. So this w get cancelled. So stiffness is given by c d raised to 4 divided by 64 r cube n. Okay, these are the different formulas you should remember while solving the problems. Okay, let us take one example. A closed coil helical spring is required to carry a load of 150 Newton. If the mean coil diameter is to be 8 times that of the wire, calculate these diameters. Take maximum shear stress as 100 MPa. Okay, this is the given problem. Here a load is given, that is W is equal to 150 Newton. If the mean diameter is to be 8 times that of the wire, mean diameter is, that is capital D, is equal to 8 times that of the wire diameter, that is small e. Okay, so capital D is mean coil diameter. Always remember the mean coil diameter is capital D, that is here in this problem is equal to 8 times that of the wire, that is small d. Okay, so capital D is equal to 8d. So what is the radius? Radius is half of the diameter, so that is equal to 8d divided by 2 is equal to 4d. Okay, now what is this given? Maximum shear stress is given, that is tau is equal to 100 MPa, that is nothing but 100 Newton per millimeter square. Which formula you can use? We have twisting moment formula. WR is equal to pi divided by 16 into tau into d cube. Substitute W is equal to what is here? It is it is not 100. W is equal to 150 into R, capital R is 4D, is equal to pi divided by 16 into tau is 100 into d cube. D we have to calculate. So this d get cancelled. It becomes d square is equal to, simplify, you get 30.6. That is d square. So square root of d square, d is equal to 5.53. So that is equal to 6 mm. Okay, we want both the diameter, capital D also, small d also, because here it is asked to calculate this diameter. So capital D is equal to 8 times of small d. So 8 into 6 equal to 48 mm. So small d is equal to 6 mm and capital D is equal to 48 mm. So like this you can find the diameter using this formula. I hope all of you understood. We'll take some more examples in the next class. Thank you.